Okay, I hit the record button. All right, so the top person here is Joseph, and not really sure why he didn't get C. Maybe he just gave up. He must have missed something. Anyway, he knew what he was supposed to do. So I guess the question is, I said that these four problems, when I pick problems, I try to pick a theme. So the question is, do we know what the theme is? Does anybody know what the theme is? And maybe if you knew what the theme was, you may be able to solve B without run too long. Any guesses on what the theme is?
Wasn't the theme still search?
That's half of the theme. There's the other half. Okay, let's look at this first. Problem A, the one that I guess Jana and Luke and is there anybody else other than Joseph? Yeah, okay, so the three people solved. So okay, so you're trying to paint. So I'm going to skip right to the input. So you have N, which is 100,000 number of paint can sizes. And then M is the number of colors that Joe needs. Each of the next N lines contains the size of a can offered by the paint shop in microliters. No can contains more than 1,000 liters. So you have to remember though, this is microliters. So microliters is 10 to the 6. So 1,000 liters times 10 to the 6 is 1 billion. So we're still okay with integers, 32-bit int. The next M line contains the number of microliters that Joe needs of a given color. It's guaranteed that for each color, the paint shop sells a can large enough to satisfy Joe's needs. So the idea is that let's look at here. So the paint store sells 3 sizes, 5, 7, and 9. But Joe wants to buy a can of size 8, size 6, and a can of size 8. So there isn't size 6 and size 8. So to waste the least amount, he's going to buy size 7 to satisfy the 6 and size 9 to satisfy the 8 for a grand total of 2 microliters wasted. Okay, so basically what you have is you have this list of available can sizes. And then you have the request, right? So when you want to request, let's say you want a 6. Well, you look at this list and you say, can I satisfy the request exactly? Right? If you can, then you do that because then there's no waste. But if you cannot, then the best thing that you do is to look at the next biggest one, right? And then you figure out how much is wasted based on that. You would never want to get anything that's bigger than the next biggest one because you waste more. Also, they tell you that it's guaranteed that for each color, the paint shop sells a can large enough to satisfy Joe's needs. So you're not going to be asked to have a request that's like 12 because there are no cans that can satisfy. Okay, so that's the problem. You're given a list of available can sizes. You give a bunch of requests. For each request, you have to find the smallest can size that is at least as big as your request, and then you sum up all the wasted microliters. Okay, so I'm going to put Jana and Luke on the spot. Maybe I'll put Luke on the spot first because he took a few more tries to do it. So Luke, why were you getting bad submissions for the first few times? Were you getting run too long? Were you getting wrong answer?
I was getting wrong answer because I needed the long int for my end answer.
Okay, because when you sum up all of the wasted. Okay, so let's go back.
Yeah, when you sum up all the waste, then it was going too big, and I didn't notice that till try 4, I think.
Right, there's 100,000 of these requests. In the really, really bad case, it could be that the request is 1, but the can size in the worst case could be up to a billion. So the waste, it's of course 999,999,999, and you multiply that by this many requests, and then that's going to be longer than a 32-bit integer. Okay, so yes, long. So that's the only, is that the only problem you had?
I think so. I think my first submission would have been right if I did long.
Okay.
And then I tried some other stuff, and then I went back to kind of what I was originally doing, and then changed it to long, and it worked.
All right. Okay. So, what is your idea? What is your algorithm?
So I have a vector that stores the shop paint cans,
Mm-hmm.
and a vector that stores Joe's paint cans,
Mm-hmm.
and then I get that information. Then I sort the shop vector, and then I go through Joe's vector, and then I get the lower bound of that for each of so I get the lower bound based on the shop vector, but using each element of Joe's vector, if that kind of makes sense. So
Okay.
yeah, so in that list, I'd have I'd use 3 and get the lower bound to 3 using that list, which would be 5, and so on and so forth. And then I just kind of waste plus equals whatever the difference of that would be of the
Okay.
lower bound.
And Jana, what about you? How did you do this?
I also did the same thing. I used lower bound because Luke reminded me about that, and I
Oh.
knew going in of his mistakes. So
I see, you were working
mine's
together.
pretty similar, yeah.
Okay, so can you tell me, okay, anybody tell me, what does lower bound do?
It gets the first number equal to or greater than the number that we're searching for.
Okay, the first place that is greater than, so first position greater than or equal to X. Okay, so that's actually exactly what you want, right? But can you use this? Can you use lower bound on any array?
No, it has to be sorted, right?
Right, so you said sorted. So why do you have to sort it?
Because
is-
does it use binary search?
Because this is binary search. Okay, so if you're using binary search, you must have it sorted. So if you think about, so let's think about the complexity. Sorting the shop vector, the n of them, sorting is n log n. Okay, 100,000 n log n is nothing. Then down here, there are m requests that you have to do. And then the binary search, each one is log n. Again, both of these numbers, m and n, are at most 100,000. So again, it's nothing. And that's why this is fast enough. So the point is that you use lower bound if you have a list that's sorted to quickly find out where the next smallest value is after X. Okay, that's essentially your answer. So the main thing, I suppose, is that this shop vector, it's the same for multiple requests. So you can afford to do this once, right? If they give you this different list every time a request comes in, then it may no longer be the best strategy to sort every time. Right? The most important thing is you sort this once, and then after that you can keep using binary search. Okay. Okay, so that's kind of a warm-up question. Any questions or comments before I move on? Okay, so I said, what is the theme of this set? People talk about search, and I said that's only half of it. The other half is binary. So the theme of today is binary search. All right, so let's, I don't know if you even need to see my code, but here's my code. Okay, so I have a list, I have an array. You can use a vector, doesn't really matter. Sort it. Then for each of the requests, I read in the request. I call lower bound to find out where it is. And okay, so one thing that's a little bit of a detail in C++, in the STL, when you use lower bound of minimum elements or all those things that finds something in an array or container, it doesn't actually return the element. It returns an iterator to the element. So to get the actual element, you need to start, okay? And then I subtract X, that would be the waste. Now, one thing that you have to be a little bit worried about whenever you do this is, would this somehow be returning the end? Right? So remember, you have an array, or whether you have a vector array. I use an array, so the start is here, and the end is the end, the imaginary element, one past the end of the container. And it's possible that lower bound return this spot. And that's possible if X is bigger than everything in your array. Okay, and in that case, when I start this, it will possibly crash your program. That's the best scenario, otherwise it'll read some garbage. But the reason why you don't have to worry about it here is because they told you that this can never happen. They tell you that for any request that you make, there must be at least one can that has that size or more. So you don't have to check for that. But in general, when you call lower bound, upper bound, or whatever thing that you use to search for something, you have to worry about the possibility of it returning an iterator of this imaginary elements one past the end. Okay. All right. So that's just a minor detail that doesn't really apply here, but in general, it's good to think about just in case. Okay, Firefly. Okay, so you have a picture like this. The cave is n units long, n is even, and h unit high. So here there are 5 units high and 14 units across. Okay, so there are 14 of these spikes. They always start from the bottom and alternate, one from the bottom, one from the top, one from the bottom, and so on. And what you want to do, okay, a firefly, it's going to try to fly any one of these directions. Okay, just a minute. I need to somehow find a way to mute my dog here. How am I going to do that? I'm not sure. Just okay, so you can choose one of these lanes to fly. So if they're 5 units high, you can fly any one of these. And if you fly, let's say this way, then you knock off 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is 8. If you fly here, you knock off 1, 2, 3, 4, 5, 6, 7, and so on. And they say that if you, for example, fly down here, then you destroy 8. Anyway, they said that you want to find a level so that when you fly through this, you have to cross as few obstacles as possible. So it says that there's a way you can do it with only 7 obstacles. So you're given the width and length of the cave and also the size of all obstacles. Actually, I think they mean height because they talk about length and height. So I think that given this should be height. Given the height and length, write a program that determines the minimum number of obstacles the firefly needs to destroy to reach the end of the cave, blah, blah, blah. The first line contains 2 integers n and h, and it's up to 200,000. It's always even. the height is up to 500,000. And the next n lines contains the size of the obstacles, one per line. All sizes are positive integers and less than h. And then you have to output two integers separated by a single space on a single line. The first number is the minimum number of obstacles the firefly has to destroy. The second is the number of levels on which that can be achieved. So maybe there are two ways. So here they say that if you fly, and the first, if you fly here or here, you can knock up 7, it says. And that's the best way. Okay, so that's the question. So I'm gonna put Luke and Jana on the spot, whoever wants to say something, how you try to do it.
So I looked at yours, Howard. I think we both did this different, but that instead of like I didn't separate top and bottom. I just did like if it's if divided by 2 it equals 0. So like if it's odd or even. And then
Okay, that doesn't
okay,
matter.
and then I had a certain like I used an array for the different levels. And then basically if it was even, then it meant it was, were we starting on the top or it starts on the bottom. So if it's
Okay, it doesn't matter which way you
yeah,
do it, right? Okay.
no, I mean for the like how it alternates. So if it was even, then it started on
Okay, yeah.
it was the bottom one.
Yeah, actually, it doesn't really
Okay.
matter. You can just flip the problem. You can just flip the problem and look it upside down. right?
Okay.
It's the same problem.
So then, yeah, for that level, if it passed through, then I would increment that the level at that number. So like at the first
Okay.
pin, I would increment the level at that number. I don't know. I did it weird.
Okay, but it was run too long, huh?
Yeah, it ran too long.
Okay, Luke, you want to say anything?
Yeah, I pretty much did like the same thing. So for the first input, if it's 3, then you have like a height array, then or level array. Then you go through the array and just increment, the first 3 elements by 1, or the first 3 levels by 1. And then you search for the minimum element. Then you count how many times that you have that element in that array.
Okay, so let me show you a couple of ways to think about. So I'll show you what I did, and I'll show you maybe a different way to think about this. Okay, so the first thing that I wanted to say is that it's probably better to separate the up and down separately. Okay, we'll worry about how to deal with, let's say, we'll worry about how to deal with the things that are going down. We'll do the things that are going up first, because that's this one, but this is a little bit easier. Okay, so what are we going to do? We're going to try going at the bottommost level, then the next one, then the next one, then the next one, then the next one. Okay, so if you're going at basically the lowest level, how many are you going to cut? All of them, right? There's no way to avoid cutting any of them. So if you are going at the bottom level, you will cut all of them. The bottom, right? You agree?
Yeah.
Okay, now let's look at the next level. Who is not going to be cut? Basically, if this is a 1 and this is a 1 and maybe there's a 2 and 2 and so on, when you go to the next level, who is not going to be cut? The only ones that are not going to be cut are the things that are less than you, which is 1. Yes? So if you know how many 1s there are, as you go up the level, you can decrement that count. Similarly, when you see how many of these cross there, you can decrement from here to here, you can decrement how many 2s there are, and so on. So if you have a quick way to figure out how many 1, 2s, 3s, and so on you have from these bottom picks, then you can fill up your array. I guess you can have an array that basically goes through the levels. These are the levels that you fly. you can quickly feel how many of the bottom ones are cut by flying at each of these levels. And each time you go from one to the next one, you take the previous number and you subtract the number of things that are in that range, right? So if they're, when you go up from 1 to 2, you look at how many things have 1. You go up from 2 to 3, you look at how many things have 2, and you decrement it. Does that make sense?
That makes a lot more sense.
So what about this way, right? This going down is pretty much the same idea, right? Look at how many of these things, look at how many there are. That's the total number of things will be cut if you fly this way. What about this one? Well, it's the number of things here minus the number of ones, minus the number of twos, minus the number of threes, and so on. And then once you know how many of the top ones you've cut at each level and how many of the bottom ones you cut at each level, you can combine them, right? You can just go through the two arrays in parallel and just add them to the numbers and then figure that out. And because there are, so this process of computing this, basically assuming that you know how many things there are in the bottom and how, you know, how many things, how many ones there are, how many twos there are, and so on. If you can get that quickly, let's say order one time, then this whole process of computing this can be done in big O of h time. And h is up to, what is it, 200,000 or something like that. Let me just quickly check. This h is, 500,000. But anyway, 500,000, it's not that linear time. So now the question is, how do you figure out how many ones there are, how many twos there are in constant time? Well, there are many different ways, but because there are only 500,000 heights, you could have a height array, basically height array. I don't know what you call it. Height counts 0, 1, 2, 3, up to, I don't know, 500,000, let's say. And then initialize them all to 0. And every time you read a height that's on the bottom, you can do a plus plus. So you can just, every time you see a 1, you just increment this by 1, plus plus, and then you see another 1, plus plus, and then you'll be able to count quickly. You can do all of this in constant time, basically. Does that make sense?
Yeah, so we don't have to sort it at all then, right? You just iterate
Well,
through and
okay, this is actually a different way of what I did compared to what I did. So I'll show you a different way.
okay.
I mean, you can sort it. You can sort it. Sorting it might help you to answer this question too.
Okay.
Okay.
So this would be considered like divide and conquer then, right?
There's no, I don't think there's any divide and conquer here. So normally divide and conquer, you split up a problem in multiple parts and then solve the problem recursively and then combine them. Here, we don't have any of this recursive thing,
Oh, okay.
right? We just split it up into 2 parts and that's it. So normally divide and conquer, there's a, it's not just splitting it up once, it's splitting it up and recursively splitting and splitting it.
Okay, makes sense. Thank you.
Okay, now, believe it or not, I actually only came up with this idea while I'm talking about it just now when you told me what you try to do. Because what I did was completely different. Well, it's not that completely different, but it's a bit different. So what did I actually do? So again, I split the top and bottom and process it differently. Okay, but so I'll just show you what I did with the bottom. So I sort the bottom. Okay, so I might have a bunch of 1s and then I might put some 2s and then I put, maybe I don't have 3s, I have 4s and so on. Okay, so I sort the bottom. Now, if I want to know if I'm flying at a particular line and I want to know how many I cut, what do I do? What do? I do a binary search with lower bound again, right? Because if I'm flying at the location 2, but let's say there are no 2, maybe this is 3s. Well, then basically, once I figure out the lower bound, it'll give me this spot, and that will tell me how many things are remaining in my sorted list, and those are all the things that I cut. And that's it. So I use binary search when I first saw it, but I guess you also don't need to use binary search. So
Would it be quicker theoretically to use binary search though?
No. In fact, what I
Okay.
showed you before was a faster algorithm, because
Okay.
the binary search here, I should do a basically binary search for each of the levels, so H and then log n. That's the binary search algorithm. What I had before with this is big O of H plus n. So plus n, this is to read the inputs and set up that frequency array, and then H is then as I'm stepping through the height one by one, and I just get rid of the number of things in each height level. So this is the binary search algorithm, and this is the I don't have a name for it. I don't know what do I call
Array
it.
algorithm or something.
Incremental processing, I guess. Yeah, whatever. The first algorithm that we talked about. So this is actually better. So, but that doesn't fit the narrative. That's why I guess I use binary search everywhere. So where is my code? Is it here? No. Hang on. The problem is the caddis thing is it's covering the tab thing, so I can't select it easily. It's not this one. Is it this one? No. It's this one. Yes. Okay. So what did I do? I read in N and H. Then I have a bottom and a top. Okay, so maybe this is another minor thing. So when you have a vector, okay, so when you have a vector V, and you know how many elements there are. So one of the things that you might want to say is, well, maybe there are 500,000 or whatever number of elements. So what I'm going to do is I'm just going to write the standard loop, I less than n, I plus plus, and then I don't know, C in arrow LX, and then V dot pushback X like this. Okay, this is probably code that many people will write. But instead, what I'm doing is I use reserve, which basically kind of resize things internally, but it doesn't actually, when you actually ask for the size of the array, the vector, it will actually tell you 0. Okay? So reserve just allocates space internally, but don't commit to actually using them yet. And then I do the pushback. So what is the difference? The difference is because I know exactly how many elements there are going to be, I'm actually just making sure that I have enough space here. And I'm allocating all this memory in one go. So I'm not, if I do it this way, then every time I call pushback, there's a possibility that it's going to go and allocate memory. And every time if you have a vector and you want to grow, what is it going to happen? It's going to allocate a bigger chunk of memory. It's going to copy all the old stuff over. It's going to deallocate. Okay, so copying, it takes time. And if you have a large array, even though STL try to be doing things a little bit more optimized, this can be slow. And by reserving, that means that I don't have to do all of these allocations in the middle. It will have to space all at the beginning. Alternatively, I can actually just put this in the constructor. So I will allocate the vector of the right size. And then instead of using pushback, then I would have to say bot I equals to something. But then I have to remember that even though I goes from 0 to n, I have to remember that I'm using only half of I because I'm splitting the list into two halves. So either way is fine. But I guess the main thing is if you can avoid allocating the array growing things at every step with pushback, if you have some idea of what the size is going to be, then you should tell STL to give it a hint and make it go faster. Okay, so that's really the minor point. Then I sort, and then basically this is what I did with the so this is okay. Wait, this upper bound. Oh, I'm then doing something a little bit different than what I said. Okay, so so I have this list, this sorted list, and I'm trying to shoot a line here. So upper bound is the first number that's bigger than it, because right. Okay. Oh, but then I'm using upper bound on h minus 1. So what am I trying to do? So if I'm shooting here, if I'm shooting at h, I'm looking at h minus 1, but look for the upper bound, the first number that's bigger than it. I'm not quite sure why I did upper bound instead of lower bound. Maybe just for variety. Who knows? Anyway, so then I figure out how many times it crossed the top, how many times it crossed the bottom. And then I have a map that keeps track of how many times I see each cross. So maybe I see 7 3 times. So I just answer of 7 is plus plus every time I see 7 plus plus. And then a map is sorted by the key. In this case, the key is the number of crossing. So the begin of the map is an element in the map that points to the one with the smallest number of crossing. And when I start, that would be the element, and that picks it apart. Each element in your map has 2 parts. First component is the key. Second component is the value. Key is the number of crossing, and the value is the number of times I see that crossing. Okay, so that's kind of my that's STL trickery to get things done. Okay, so that's how I did it with binary search. Any questions? Okay. Now I'm going to skip to the 4th problem because I think it's actually a little bit easier to look at. Okay, so it's easiest if I just show you what the problem is. Okay, so here you have 5 and it comes in 2 lines. So let me just write 2, 1, 8, 2, 8, and 9, 9, 4, 1, 4. What you want to do is you want to move these things around so that at the end, if the same numbers are next to each other, either on the top row or the bottom row, there's no need for the top row and bottom row to have the same numbers. So for example, you can decide to move 1. So you can decide to move 1 like this. When you decide to move something, you can pick it up and move it anywhere. Okay, but now that's still not good enough, right? But actually, if you move the 1 the other way, maybe you move the 1 this way, now at least the bottom rack is okay. Okay, but the top rack is not, so you might have to move the 8 to here and maybe the 2 to here. And if you do that, the heaviest thing that you move is 8. Okay, now it says that the heaviest thing that you have to move is 2. So how do you do that? Well, you can move the 2 this way and the 1 this way, and that will give you 2, 2, 1, 1, 8, 8, 9, 9, 4, 4. And everything comes in pairs. And in this case, the heaviest thing you have to move is 2. and that's preferred. So you want to minimize the maximum weight that you move. Okay. So in this case, in the second sample case, everything is already paired up. So there's nothing to move, so the answer is 0. Okay, so that's the problem. Any idea? Well, okay. Other than the word binary search, of course, binary search is here. So the question is, how does binary search figure into this? Anybody have an idea? Okay, so this is a binary search in a little bit different way, right? So in the first two problems, binary search, it's the standard thing that you learn about in your whatever class you learn binary search from. You have some kind of a container with sorted stuff, and you want to look for things that are either in the array or just next smallest thing, next biggest thing. That's the standard binary search. But here, we're looking at a different type of binary search. We're doing binary search on the answer. Okay, what is the answer? This is the answer. We're going to do binary search on the answer. What does that mean? Okay, so let's look at this. So I have this problem, and let's say that the weights are, doesn't matter what they are. Well, okay, in this case, actually, it's kind of bad because everything is guaranteed to have to be moved. So let me just change the numbers around a bit. Okay, maybe something like this. In this case, if you move 8, 1, and 2, you can do it. I don't know if there are any other ways you can do it. But anyway, if the problem is not already solved, so meaning that if the things are not already in pairs, then the answer it's greater than 0. You must move something. Okay, that's kind of the obvious thing. But if things come, you can easily check right away that if things comes in pairs already, then the answer is 0. There's nothing more to do. So the normal case is if the problem is not already solved from the input, then the answer is greater than 0. Also, you know that the answer it's less than or equal to the maximum weight possible. Because if you move every single weight, you can always do it. Okay, so in this case, in this problem, the max weight is 9. Okay, so you can always move every single weight to put them in pairs. So if you look at the continuum of possible answers, I guess I shouldn't use the word continuum because these are integers. 0, most of the time, it's no, you cannot do it. The max weight in this case is 9. The answer is yes, you can always do it. Okay, and now you ask, okay, what if you look at somewhere in the middle? Okay, is it true that if the answer is no, so if you cannot solve the problem by moving only weights of size 5 and under. Okay, so let's say that you're looking at all the weights that are less than 5, well, less than or equal to, you're allowed to move all the weights that are less than or equal to 5, and you cannot do it. What if then, if you know that this is no, what if I ask you, can you do it if I just allow you to move weights less than or equal to 3? The answer is, if you cannot do it by allowing you to move weights 1, 2, 3, 4, and 5, then certainly by making it more restrictive, you will still see no. Does that make sense?
Yeah, that makes sense.
And likewise, if, let's say, allowing you to do weights less than equal to 5, the answer is yes, that you can put things in pairs by moving only things 1, 2, 3, 4, and 5. Then if I ask you the question, can you put things in pairs by moving things 1, 2, 3, 4, 5, 6, 7? The answer is also yes, because you can just decide not to move 6 and 7. Does that make sense? So this is kind of important, okay? If you know that the answer is one way, let's say no, then somehow that forces the other side to be also no. And if you know the answer is yes, it also forces the answer to be yes. This allows you to do a binary search on this range of answers. So you ask, take the middle, right? So this is 9 in our problem. This is 0. So I ask, what's the middle? Middle, let's say it's 5. I ask if I can easily say by moving all the weights from 1, 2, 3, 4, 5, can I put things in pairs? If the answer is yes, then I know that the best answer is 5 or less. You know that 6, 7, 8, 9, all of these are yeses, but you want the smallest one. So you don't want any of these. So now your max is now in this part, and you can do binary search on this again. And so let's say you take the middle and 3. If the answer is no, you cannot do it. That means that the answer cannot be any of these. So now you try 4, and then I don't know whether it's yes or no, it doesn't matter. But the idea is that when you do this in a binary search, at some point you would discover the yes and the no, the 2 pointers that you're looking at, the low end and the high end in the binary search, will eventually be next to each other. And at that point, you can stop. And when you stop, if the answer, what you're looking for is the smallest one that's yes, then you output high. If the answer is looking for the largest one that is no, you put low. Okay, so it's always important to be very, very clear on this. When I always draw a picture, even though I've done this millions of times. I will have a low and a high at the beginning, which is, let's say, 0 and max weight. And I always make sure that I know which end is yes and which end is no, because it depends on the problem. Okay, so for this problem, the high is always a yes, and the low is always a no. And I can say that low is a no only if I remember to check at the very beginning that 0 is not an answer, because it's possible that 0 is an answer. They give you a sample example. So if 0 is an answer, don't even go into this binary search. You already found the answer. And then you would say something like this: wow, high minus low is greater than 1, so they're not touching each other. So this type of problem, just to show, maybe just say one more thing. This type of problem always, there's sort of a range, some unknown range that's always a yes, some unknown range that's always a no, and at some point it switches from yes to no. And in this type of problem, either you're asking for what is the value that gives you the smallest yes, or what is the value that gives you the largest no. Okay. So anyway, what do? So you do something like mid equals to low. Okay. So how do you if you know the value of low and high, how do you compute mid? Do you know? How do you compute the middle given low and high? I think I talked about this once before.
High minus low divided by 2.
Plus low.
Right.
Don't forget about plus low. Okay, so this is, I mean, if low is 0, then it doesn't matter. But at some point while you're doing this binary search, low could be something like 7, and high could be like 100. And then you have to do high minus low divided by 2 and then add low. Okay, so this is the right thing to say. Another popular thing that's wrong, and I think I said that once before. Oops, why am I? Oh shit! Wait, what did I just do? Am I still showing the screen? No. Okay, let me share the screen again.
No.
Okay, my pen was touching. Okay. So what you should not do is this. Okay, so why is it bad? I said that one before, and basically, if high and low are really high, they're really big numbers, then low plus high can overflow. And then you end up with some negative number that's completely out of range. Anyway, okay, so mid is equal to low, high minus low over 2 plus low. And then you would say if you have some function to check if it's possible, and it will return yes or no, right? So it will return yes or no. And this is where I remember which n is which. So if mid is, if it's yes, then I would say high is equals to mid. Because if it's yes, then I want to move the high down to here. Otherwise, I want to move mid, I want to move low up. And I always make sure that low is a no and high is a yes. At least for this problem. I mean, in another problem, you might have no and yes switch, but in this problem, it's yes for high numbers, low for no numbers. And then at the end, I am looking for the lowest yes, so that would be this. So as long as you know how to write this one, this function, then you're done. So how do you write this function? Well, it's actually not too difficult. The idea is that if you're checking whether you can put things in pair by moving everything up to this range, up to a certain value, basically it means that you can take the list that you have and remove all the things that you can move, because once you decide you lift them up and move them, you can move them anywhere. So they're completely irrelevant. Okay, so let's say here. So if you decide that you want to remove 2, up to 2, so what do? You basically look at the array and ignore anything that's 2 or below, and you check for each element that remains, are they paired up correctly? And you can do this in linear scan. Okay, there are many different ways you can do this. You can, I suppose you can actually form a new list and then check every pair of numbers they're the same. Or you can do some clever indexing that you don't actually form a new list and just scan through and ignoring the ones that are removed and only count the ones that are not removed. So it turns out that I think it doesn't actually even matter which way you do it, because they give you 7 seconds of running time, and which is a lot. You can even create your list and do things. But if you don't want to do this, if you don't want to create lists and copy back and forth all the time, because that's potentially slow, let me show you how I did it. Okay, so let's just kind of go through this. Okay, so I read in the list, I read in the number, and then I have the 2 lists, the top rec and the bottom rec. I just read it in. Okay, so what's going on? Why do I have resize? Because for some, oh yeah, because I decided to use global variables everywhere. So then at this point, when I declare it, I do not know what is the size of the vector. So, but at this point, after I read in n, I know the size. Okay, so for some reason, I decided to use global vectors, so I don't have to pass them. Anyway, doesn't matter. Then I read in the top weights, I read in the bottom weights. And here, this is something that, remember, check to see if 0 is the right answer. Because none of those binary search would work if 0 is not a no. My binary search is set up so that 0 is a no. If I forget this check, this can go very badly because of the way that I set this up. Okay. Then low is 0. High is basically the maximum element of both lists. if I remove the maximum element, I can always do it. And then this is basically the loop that I wrote. And then, so the main question is, what is this check function? All right, so we go to the check function to see. So the check function, actually, I kind of break it up into checking both the top and the bottom separately. Okay, so I just write one function that will check an array, and then I check it twice. Okay, so how do I check it? Okay, so num, it's going to keep track of how many weights there actually are after I removed all the things that are less than g, less than equal to g. And then last is somehow the last thing that I saw that hasn't been removed. So at the beginning, I don't have anything that I've seen. Okay, so I go through the array. If the element is less than or equal to g, that's the way that I can move. So I just skip it. I don't even care. Then I basically say, how many have I seen? If it's odd, right? So the number of things that are actually remaining, my number is going to be 0, 1, 2, 3, 4, 5. So this is the scheme. So if I'm at this position, there's nothing to check because I don't know what comes after. But when I'm odd, then I better make sure that when I'm odd, it's the same as the last one. So if I'm odd, okay, so maybe this is 3 and 3, and this is 7, 6, and 5. So when I'm odd, I look and make sure that if it's not the last one, then I can quit right away. So when I'm down here, I look at the last one, it's not the same, so I can say, no, this doesn't work. And then this is just sort of bookkeeping to keep track of how many things I've seen and what is the last one. And then I have to be a little bit careful because it could happen that, let's say after I remove all the things that are not, that are bigger than G, I might just have, let's say something like this left, 7, 7, 3. And the way that I would have run this loop, I would have checked this and it's okay. I would not check this because there's nothing to check, and then I'm done. And this is the odd weight out. So I have to make sure that the total number of things that are not removed is even. Because if it's odd, then there's no way I could have paired it. So that's my check. And if you look at this, right, so how bad is this? This is basically linear time, big O of n, right? And then the binary search part, okay, so the binary search part here, what is the complexity of binary search? It's big O of log of something. But this is not n, because I'm not searching in the array. The range I'm searching in is the maximum value of weight. Okay, so it's a log of the maximum value of weight. Max weight. So the total algorithm, the total cost, this binary search runs log of the maximum weight. Each time it runs linear time because the check is linear time. And what are the parameters? What are the values of these parameters? Just go quickly check. So this is 10 to the 6, whoops. This is 1 million. And this is 1 billion. Okay. But 1 billion, when you take log, it's only about log of this. It's about 30. Well, 31 or something like that. But basically it fits in a 32-bit integer, so it's going to be about 30, 31, whatever. So it's 30 million, which is not bad at all. Okay, and what did they say? It's a time limit? 7 seconds. That's more than enough for 30 million. Okay, so that's how you do this problem, and that's how binary search sometimes can come into to play. Even though there's no array to search, there's no sorted array to search. What we're doing, this is sometimes called binary search. Where should I write this? Getting crowded. Maybe I switch color so you can see better. Sometimes people call it binary search the answer. And this works if the answer that you're looking for has this structure where it sort of goes from one type of answer, so one type of property, all the nodes, and then it switches to the other type of property like this. And it works if there's an easy way to check any guess of your answer. Okay, usually it's, by easy I mean linear time. If you can do that, then you can try using this binary search the answer methodology. So this is maybe for many of you, it's something completely new. It's the idea of binary search. It's of course not that different from you know what you have seen. The code is more or less the same, but this check here, this idea that the answer that you're looking for has some kind of property that switches yes to no as you go up or go down, and it only switches once. That's the other important thing. It only switches once. There's no, it can't switch back to no at a higher number. If you have this property, then you can use this binary search the answer method. Okay, does that make sense?
Yeah.
Okay, so this is definitely a more advanced technique, okay, but it's very common in computer science. So another way, maybe this is a digression, but one of the things that maybe you don't think of computers as something that maybe you don't think of this as intelligent kind of method of solving a problem. One of the things that's actually extremely powerful in computer science is this idea that you guess the answer and then you check it. Now, this can come in many different forms depending on what the problem is. Sometimes the problem is yes or no. Sometimes the problem is, you know, looking for the smallest or biggest value that make things work, and so on and so forth. And guess is usually easy, right? You just come up with a guess, whatever that guess might be. Checking, it may or may not be easy, but a lot of times checking is, if somebody tells you what the answer is, and you just want to check, is it the right answer? Is it wrong? Not the right answer? Sometimes this is easier than actually coming up with the solution. If somebody gave you the solution and you just check if it's right, sometimes that's easier, right? Sometimes that's easier than solving the problem yourself. And you might say, well, okay, that's kind of, I suppose if somebody told you the answer, then sure, you can check it easy, but who is going to tell you this answer, right? Now, when you take, I don't know, and you probably in 3620 didn't talk about something called NP versus P. Did you talk about this at all?
We talked about it at the end. We watched a video on it.
Just a little bit, I guess. So one of the things about NP and NP complete and all this stuff, this is a little bit strange. This NP, I don't know if you remember what it means. It's called non-deterministic polynomial time. And what P means that you can solve a problem in polynomial time. NP says that if somebody gave you a solution, you can check the solution in polynomial time. You can check that the solution is actually a solution. But maybe you say, well, so what? Who is going to give you the solution? And if somebody gave you the solution already, why are you solving it? Well, it turns out that there are many algorithms where you can use this method to to actually make things faster. So one of the possibilities, where are you going to get these guesses? Well, in some cases, maybe you can do exhaustive search. Okay, so maybe there are not that many different possible answers. Just try them all. So for example, in that firefly problem, there are not that many heights you have to try, so try them all. It could be exhaustive search with some backtracking and pruning. So this is kind of what we did last time, right? Or if there's some way to structure the guesses and the properties that you're checking, it could be binary search. And then there are many other more advanced things that maybe I'm not going to talk about at all. But there are many other ways that you can guess. Sometimes it could be completely random guess. Sometimes it could be maybe a bit more structured. And so this idea of guess and check actually is because sometimes it's a lot easier to check than actually solve the problem. Guess and check is actually quite a powerful technique if you match the check with the right kind of guess strategy, right? And when I say guess, it doesn't mean that you randomly guess, right? So for example, binary search, you make a guess, you check, and that tells you what the next guess is. Okay, so that's just a sort of an aside. It's a very powerful idea that's used in a lot of places in computer science. Even though it sounds a little bit silly, just a method of solving things. Okay, so the last one problem is here. Okay, so there's a lot of stuff going on here. The problem is kind of complicated mathematically, but maybe the easiest thing to do, oh, this is also called firefly, kind of. Okay, so maybe the easiest thing to do for me is to draw a picture, and you can go and read the problem if you haven't done it already to figure out what's going on. So you have the ground, so this is a ground, and you have some kind of target, and this is the XY plane. Let's say this is X and Y. The target could have positive or negative X coordinates. It could be over here, it could be over here. Okay, that's possible. You start here. That's where you start. And you want to hit the target by figure out what is the speed you should go to hit the target exactly. Okay, so in other words, you can kind of, if you know what speed you're going, you always, so every single minute or every single X value as you're traveling, you always go up by, so how do I put this? Maybe it's easier if I go back to this. Yeah, the vertical velocity exactly 1 kilometer per minute. So every minute you go up by 1, but you can decide how far you go to the left or to the right. You can figure out how far you go horizontally. But you must pick a speed. So you have to pick a speed, horizontal speed. Then each minute you go up by 1. Okay, so if your target is, let's say, over here, then you have to figure out how to hit this target exactly by basically figuring out the slope, right? So the slope will be rise over run. And if you know that every time step, you're going to go up 1 this way, then you can figure out how many steps you must go across so that you can reach this exactly. Okay, that's really easy, but there's a problem. Okay, so why is it not so easy? Why is it not so easy? It's because there are certain, what they call, I think, shield or something, but there are certain barriers at different levels. So for example, there's this barrier 1. So there's a lower end of the barrier and upper end of the barrier. And in this barrier, your speed may increase or decrease by a certain factor. So there's a factor, let's call it alpha 1. So maybe if alpha 1 is bigger than 1, maybe you go here, and then when you're going through this part, you go faster. And as soon as you get out, you go at the old speed again. Okay, so this, if alpha 1 is greater than 1, you can go faster. And then maybe the next one, the next block here, maybe alpha 2, the next one is less than 1. And what that means is that when you hit here, it's going to slow you down. And then you go at the speed again, the normal speed. So you have to set an initial speed, and that speed will be used whenever you're not in one of these shields. But if you're in this shield, you are going to be traveling at basically the factor that they give you times your initial speed. Okay? So the question is, what is the initial speed that you set so that you can reach the target exactly? Right? So if I set this speed, then I come up short here. Right? I might have to go a little bit further this way. I don't know. I'm just kind of randomly drawing things, and maybe that's not enough. And then you have to go a little bit faster and so on. So that's the question. What is the speed that you have to choose at the beginning so that you hit the target exactly? So I think the easiest thing, maybe what I want to say, since we are talking about the binary search on answer. So this is exactly the binary search for answer on the answer algorithm. And I'm going to search with the initial speed. So I don't know what the initial speed is. If it is, okay, so if the target is on the right, then I know that my speed has to be positive. If my target is on the left, then I know that the speed has to be negative. But that's pretty much all I know. So what to do? Okay, so I'll just pretend that there are some barriers. I'm not going to draw the barriers. I'm going to have a target. So I'm going to set some initial speed. I'm just going to make a guess. And that's, maybe I get really lucky and I hit it right away. Okay, then I'm done. But I'm never that lucky. So what are the two other possibilities? It could be that I shoot too far. What does that mean? If I shoot too far, what does it mean to my initial speed? Is it too big or too small?
Too big?
It's too big. So if I shoot to the right, that means my speed, initial speed was too big. If I try something smaller and then maybe I end up to the left, then my initial speed is too small. So what does that mean? If it's too big, I want to make it smaller. If it's too small, I want to make it bigger. Again, well, this is another case where, so my range, so my answer range, it's my horizontal speed. It has some sort of a highest speed and some sort of a lower speed. I guess I'll just use high and low. And I always make sure that high is to the right of target. So it's gone too far. And low is to the left. So it hasn't gone far enough. And at some point, that is, it's going to be left, left, left. As I increase the speed, it's going to be left, left, left. And at some point, it will hit the target. And then if I go use more, it will be too high. And I'm searching for exactly this point. What speed can I hit the target? So what am I going to do? I'm going to say, well, find a range so that I'm going to find an initial high value that's always going to be too much. I'm going to find an initial low value that's always going to be not enough. And then I do a binary search. take a step in the middle. Is it to the right or to the left? If it's to the right, then I can bring high down here. Then I take another step in the middle. If it's to the left, then I bring low here. And eventually I'm going to zero in to reach the target. Okay. So that's kind of the idea. Now there's a lot of complicated math, I suppose. So it's not that complicated, but if you decide, once you decide what speed you're trying, then you have to simulate the path of this spacecraft to figure out whether it hits to the left or to the right. But once you have that, then it's just a binary search. So I don't want to show you, and I don't want to go through too much of the details, but maybe I should just jump straight into the code. Here. Okay, so the code is here. I'm reading a bunch of stuff. There's some shield. For some reason, I need to short the shield from smallest to largest. Okay, so now, what am I doing? I am actually going to set my low and high. I don't care where you are. I'm just going to say low. I want to make sure that low in my range and high to my range. I want to make sure the low is always to the left and high is always to the right. And what am I going to do is I'm going to say, let's say that I use move left at 1.0 meter per second or whatever unit it is, horizontal speed, and it's going to go somewhere. And if it's, let's say the target is here. If it is not left of the target, then I'm going to double it. Then I'm going to try minus 2.0. If it's still not to the left of the target, I'm going to try 0.4, minus 4, minus 8, minus 16, and so on. I'm going to double this every step. So basically, if I don't know a smallest value, a low that works, a common trick is to keep doubling the numbers until it works, provided that you know that there's at least a number that works. By doubling it basically means that you can reach it in log, whatever number of steps, in a log of that number of steps. And similarly, I will move this from on the other side. I start at 1, then 2, then 4, and I make sure that I have a value that is to the right of the target. Okay, I would speed high enough that I would end up to the right of the target. And then, okay, so now let's ignore this for now. Let's look at my binary search loop. What am I doing? I'm using, now this time mid is low plus high over 2, but these are double. Okay, I'm not doing binary search on integers. I'm using binary search on floating point numbers. So I can do this. I don't have to worry about overflow. And then I say, well, where am I going to end up if I use this speed? So getX just is a simulation. Where am I going to end up? If I am to the left of the air to the target, then I set low to be mid. So if I'm still if I take a step in the middle of the left, then I reset low to here. I cross this part out. If it's to the right, then I shrink the other half. And the idea is that as these two low and high shrinks towards each other, then my interval is getting smaller and smaller and smaller. And then at this point, let's say it's really, with the low and high are really close together, then I know that the answer that I'm looking for is somewhere in between. And if the two are so close together that maybe they're the same up to, I don't know, 10 decimal places or something like that, then it really doesn't matter which you print. And this is basically what I'm doing. While the two are differ by more than 1 to the minus 10, so in other words, it's basically the 10th decimal places. As long as the two are different in the first 10 decimal places, I keep going. And then after when they agree on the first 10 decimal places, then it doesn't really matter anymore. I can print either one of them because they're the same. If you want to look at it, look at how I do the simulation. This is the simulation, but basically this is it's relatively simple math, but you just have to be careful. Anyway, so this technique, it's called binary search the answer. Okay, and it's a very useful and important technique. It's one of the, so it's a little bit tricky because normally you try to think about how to solve a problem, what we sometimes call direct computation, right? So if somebody say, well, what is the minimum spanning tree? You have some algorithm that compute the minimum spanning tree directly. You don't say, well, maybe the minimum spanning tree has weight 10. Is there one? And then if there's one, maybe you try the minimum spanning tree of weight 5, right? So those are the direct computation. But what we're doing, it's indirect computation, right? You are given the answer or a potential answer, and then you're asking, is it a correct answer? Is it not? And furthermore, can you then somehow redirect your next search for the next possible answer, right? So this is a little bit different, the way that we're thinking about this, but it's still a very useful approach because sometimes things are very hard to compute directly. So in this case, actually, there's a way to compute the right answer directly by doing some analysis and then doing some math. But I've never bothered to work it out because it's much easier to do it indirectly. So this idea of binary search the answer is a very powerful one, and it's one that you should definitely keep in mind when you see problems. Whether it's programming contest problems or real life problems, because it can come in handy from time to time. And binary search, because it's binary search, usually, even though the check, as long as the check is relatively fast, it's pretty easy to code, and it's pretty efficient. Okay, so I guess that I actually go through all the problems for today. Any comments or questions? Okay. Now, for next week. Now, I think Noah was the one that I was chatting with before everybody else arrived, and he said that he's not so great on probability and counting and so on. And when people say that, that means I'm going to torture them with more problems of that kind so they can get better. So
I am also bad at that, so I would be down
Okay.
for doing those problems.
Okay, so you're asking for torture, so I will pick a set that does some of these probability counting, that kind of problems, and we can talk about it next week. Sounds
Sounds
good?
good. Thank you.
Any other question? Let me